This is the class that never ends. Yes, it goes on and on, my friend, and it probably does feel like that. But let's do an example that's going to be a little longer than the other one because we're going to actually look at the data. And I want to do it in Excel so that you can actually see the numbers and the data and where it's all going. I have here 3 different kinds of homes. Some homes are made of wood, and some homes are made of brick, and some homes are made of steel. Why are we making homes out of steel? Look, it was either that or like glass, okay? Give me a break. I just need an example. So I'm going to put the data in this tab. This tab I'm going to use for the table. And let's go ahead and we're going to color these with the color scheme that we were using before. I mean, in real life, people don't actually color their ANOVA table, but this will help show the pattern that we were looking at. And here I'm going to do my ANOVA test. I have 3 different kinds of houses. So right here, I could write that the averages all equal each other, or I could write it in words that they're all the same on average. I didn't really say what this data was about. What we're doing is building a home out of these 3 materials and then putting them in a wind tunnel to see how long they stand up to the wind before they fall down. So I could also put that changing the type of home from wood to brick to steel does not change how strong it is in the wind. In other words, how strong it is in the wind is not related to what the home is made of, or that the 2 variables are independent. And I'm just going to leave it here because it's the last one I did, but any of those would work as a good example of a null hypothesis. The alternative as the opposite. But be careful not to use this as your alternative because that's not the same as the opposite of all of them being equal. The reason is you could have that mu1 and 2 are equal, it's just not equal to mu3. Or maybe mu2 and mu3 are the same, but they're not equal to mu1. So don't try to put the alternative into symbols like this because you have to account for every possible way that that alternative could be happening. You have to have a sentence here that describes that changing what home material you're using does not change how strong it is in the wind. Something to that effect. Let's use our classic 0.05 here for the alpha. And now let's come back to our data. I want the overall X bar for each of these. So what am I going to do? Average all this data here. I could also add them up and divide by how many there are. That would require me to count how many there are, and I haven't done that. Let's do that. I need an n. And not just an overall n. This is an ni for each one because each one has a different amount. 6, 5, 1, 2, 3, 4, 9. All right, and it occurs to me that these sample sizes are small. If you recall, to do the ANOVA test, we have to know that it's normally distributed, and we don't have at least 30. So I'm going to come over here and insert, assume normal, and also assume equal variance. Okay, now I can go ahead and do my ANOVA test without worrying about the assumptions because I just said don't worry about them. I need an X bar I, because this isn't the overall X bar, it's a different X bar for each one. So I'm going to want to average just these ones. It should be close to that 21.5, but off some, not super close. Okay, it looks like the steel rooms held up against the wind very high, wood low. I'm guessing this might end up rejecting the null because it doesn't look like these averages are the same. But we also don't have a lot of data. So don't jump to conclusions. Let's do a standard deviation, different for each group. And now, while I'm being recorded, can I remember the right command in Excel to do a standard deviation? If I can't, I can always just back up the video. You guys never get to see the things I do wrong. There's all our means and our standard deviations. So this guy has an average that's really far out there, but he also has a standard deviation really far out there. So that means we can be less certain about the accuracy here. So it may not be reject after all. Let's talk about getting our SSG. That was the top row of the ANOVA table. That's the one we've been coloring red. And to start with, I'm going to do it the same way that I was doing it in the last video. N times this guy's average minus the overall average squared, and then the other n, and this guy's average minus the overall average squared, and this n times his average minus the overall average squared. Let me check that I didn't forget any squareds or minuses. Oh, value. That's bad. Oh, it's because right here I put A9 as the overall average when it needed to be A10. There we go. It's right here. I put A9 as the overall average. That's the name X bar, but the value X bar is right there. We have an SSG value. Let's do this again a different way, where I calculate the SSG for each person individually. So I'm going to take this guy, his average, which is down here, minus the overall average right there, and square. So that's what it was for him, and for all the other 6 people, 1, 2, 3, 4, 5, 6. So that's the SSG piece for each of these data points. For these ones, I want to take their average. Oh, I forgot my parentheses. Their average minus the overall average and squared. And that was true for 1, 2, 3, 4, 5 data points. The last one is his average minus the overall average squared, and that is for all 9 pieces. To find the total SSG thing now, all I have to do is add up all these pieces, and hopefully I get the same answer, or else I'm going to have to redo the video. Nope, we're good. I know this is long and drawn out. What I hope you see is that this is going to be essentially the same thing as just taking 6 times this little difference the first time, which is exactly what we were doing here. 6 times X bar 1 minus that guy squared. Sure, do it 1 by 1 or just multiply it by those values. Okay, I'm going to shrink those columns so that I can talk about SSE. How do we do this? I'm going to take n minus 1 times this guy squared, and then do that again. N minus 1 times s squared, and n minus 1 times s squared. There is my SSE. Let's see if we can do it piece by piece and get the same thing so that I don't have to go back through a video. It is this guy in particular minus his average squared. Okay, and I'm double checking with myself. The way I'm checking myself is saying, I want to know how far he was from his average. Okay, yeah, this makes sense. And I do that for all 5. Before they were all the same number because we were looking at the average of that group. Now we're looking at individual data points. It's going to be a little different. This guy is going to be his value minus his average squared. And that for all 4 of him. Last guy is his average, well, his value minus his average squared. And if you know Excel, you notice that I forgot to lock the X bar, which gave me the wrong answer and it didn't match up. And so I had to pause the video and figure out. Now I can go back and make sure that I do this correctly. It's this guy's value minus his average, but putting those dollar signs is Excel's way of saying lock it. So good, now I'm comparing him correctly. And this is how when I do the sum, I get the right number. Good deal. Now you might be asking, what do these values have to do with the simpler way that we were doing SSE? Well, if I wanted to find the standard deviation, I would start by adding these guys up, divide by n minus 1, and then I would want to take the square root of that whole thing. Square root of that, and there is not the 8 that I get right there. Really? Man. Oh, it's my n minus 1. I put 5 minus 1, but 5 is what you get from n minus 1. 6 minus 1, 64, and there is the 8 that we're supposed to be getting. Same for these guys right here. Sum of these pieces, if I divide by 5 minus 1 and take the square root of that, I get the 5, which is right here. So that's why using these S's is doing the similar thing as taking each data point minus his value. I had to do the last one just to check myself. Okay, let's move on to SST. And of course, the easiest way is going to be adding up the SSG and SSE, but we can also do it one by one with each data point. I'm going to take this data point here minus the overall average, and I want to lock that so that number doesn't change, and square it. What did I do wrong? Oh, I didn't have an open parentheses. Thank you. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, 6, 7, 8, and 9. And all I need to do is sum these up, and I get the same number, 14763. Yay! Now I'm ready to put these into my table. There we are, my degrees of freedom. I have 3 groups, so 2 degrees of freedom. For error, let's see, I gotta go back and figure out the total sample size. Let's see, it was 20. So this is 20 minus 3 groups is 17. 20 minus 1 is 19. 2 plus 17 adds up to 19. We're doing good. This is going to be this guy divided by that one, and the other one divided by that one. The F-test is MSG over MSE. There's our 3.13, which is what I need over here. Value. Oh, let's just paste the value there. Now let's find us a p-value. Switch to the F. Oh, I did not look at my degrees of freedom. 2 and 17, right here. 2, 17, and it's always this sided. What was my F value? I get that you're watching this video like, oh, didn't you just have that a second ago? Hey, I paused this for a few minutes, make sure everything's right before I keep recording. So have just a little patience with me. 0.06978. If you recalled at the beginning of the video, I said I bet we're going to reject because those means are different, but it turns out this has failed to reject, which then means we cannot show wind strength depends on home material, or we cannot show a relationship between wind strength and home material, or we could not show that wind strength is related to home material. Lots of different kinds of wording you can use. That's surprising because it looked like the averages were even. I could also say we can't show that the averages are different, and looking here, it looked like they were different. The problem is you just don't have enough data. This is a high average, but with a lot of standard error there, we would need more data to prove it.